All right, ladies and gentlemen, this class recording has started. So, Chapter 2 and Chapter 3 deal with kinematics. And we talked about kinematics being a description of the motion, but without really talking about why it's happening, right? So we're just describing that motion. And Chapter 2 and Chapter 3 have introduced us to several terms that we can use to describe the motion of the object, right? Things like, position, that tells us, fill in the blank. Position tells us where something is, right? And things like velocity, that tells us direction, but it also tells us speed, right? How fast something's going, which way it's going. And we have to include a time factor in there to, at least calculate the velocity. And then in Chapter 3, we were introduced to the concept of acceleration. So like we talked about on the first day of kinematics, where an object is, what it's doing, what's going to happen next, and then, when are all these things happening? If we can figure out these things, or if we can measure these things about a motion, we do a good job of describing it. But as we look a little bit more closely about how we define velocity, how we define position, how we define acceleration, we find out that certain relationships start or continue to show up between position, velocity, acceleration, and time that we can use regardless of how big the acceleration is or how big the velocity is, but all four of these things are related because we use certain ones to define other ones. So we'll start that discussion with this ramp. Here is a ramp. Up at the top of the ramp, this ball starts with 0 velocity. It's resting up at the top of the ramp. And I will tell you that this ramp is tilted in a way that the ball experiences an acceleration of 3 meters per second squared. Sorry, you don't have this on your picture, but just using it to get into something. All right. The fact that the acceleration is 3 meters per second squared tells us what? What does acceleration tell us? Go ahead. In a second, we'll be going. Go ahead, Brad. You want? Okay. In this case specifically, our velocity is going to increase by 3 meters per second for every second that goes by. In this case specifically, because as it rolls down the hill, what's happening to its velocity? It's increasing. But more generally, if we have an acceleration of 3 meters per second, that means that the velocity changes by 3 meters per second for every second that goes by, which is different than something moving 3 meters every second, right? So, that being the case, if it started off at rest at time equals 0, by the time we get to 1 second, how fast will it be going? 3 meters per second. And the following second that goes by, 6 meters per second. And then 9 meters per second here, 12 meters per second here, and 15 meters per second by the time it gets to the end of the ramp. Okay? So its velocity continually increasing. Right? And we looked at, again, you guys don't have this picture, but if we looked at a velocity versus time graph for that motion, what would it look like? right? Okay? That velocity continuously increasing, you know, each second that goes by, the velocity getting higher again and again and again, right? Way back in pre-algebra or whatever, right? We learned that that equation represents any straight line. And like we did in the first chapter, or chapter 2, we can apply this equation specifically to, or we can apply that equation generally to this graph specifically, right? For instance, what's one piece of information we know about that equation as it applies to this graph? Right. The slope represents the acceleration, right? So the slope on a velocity graph represents the acceleration. What else? Simran? The y-intercept is 0, but more generally, that's for that picture specifically. More generally, what would the y-intercept represent? It was at rest in this one, but more generally, it represents the initial velocity. In this case, it was 0, right? Because it started at rest up, or in the case of this ramp, right, it started at rest up here at 0, but in general, that y-intercept would represent the initial velocity, right? What are we measuring on the x-axis of this graph? Time, right? So time takes the place of the x variable, and then that means that the y variable would represent the final velocity. So here we have a nice linear equation that relates together how fast would an object be going at a certain moment in time if we know how fast it started, the acceleration, and for how long it accelerated, right? So that is our first kinematic equation that relates together different aspects of a constant acceleration motion. Brett, go ahead. Yep, just has it in a different order, right? So here, 3.2, motion with accelerated, or motion with constant acceleration. The first equation that comes up is the velocity time equation, right? And here, this equation is basically the same equation, just rearranged a little bit, right? Again, we just, did VI plus A times T instead of AT plus VI. That's the same thing. We add, and it gives us the same answer, right? It's just in a different order. Well, the reason I did it this way, the reason that I did it this way is to show you that that equation really is just representing this straight line, right? And the different general aspects of this equation apply to our equation. But this and this are exactly the same thing, right? Same equation. Good there. Okay. Next thing that I want to talk about takes us back to this graph. Okay. Perhaps you remember, hopefully you do, that the first day of acceleration, I showed you a picture that showed a guy riding his bicycle. And it showed the position of that guy on his bicycle at consecutive seconds, right? Where he was 1 second after he started, 2 seconds after he started, 3 seconds after he started. And much like the positions in this picture, he kept getting farther and farther and farther every second because what keeps happening to his velocity? It was increasing. If you go faster, that means you go farther each second. And that's what that picture showed us. But you may remember, and if you don't remember, I should just show you, that on page 74. There it is. On page 74, up at the top, right, here's this guy riding his bicycle, and the successive pictures keep getting farther and farther apart. But here, at t equals 0, we have a velocity of 0. But then at t equals 1, we have a velocity of 2. So we could then assume that the acceleration was 2 meters per second squared, right? But then down here, when it shows us the position, right? He only went 1 meter during that time. And some people looked at that, I remember, and we were a little confused by it. Okay? But when we think about it now, we'll try to explain this a little bit more. So you know what? I'm going to use this picture of the guy on the bicycle instead of the picture of the ball rolling down the ramp. So look at me adjusting on the fly like that. So I'm going to go here. Alright. So here's this guy on his bike. Oop. Unzoom you. Alright, so it tells us that the velocity initially was 0 and the velocity at the end was 2 meters per second. How come he doesn't go 2 meters during that second? Luke, go ahead. He was gradually increasing to a speed or a velocity of 2 meters per second. In order to go 2 meters in a second, you would have to be going with a velocity of 2 meters per second the entire time. And that wasn't the case here. He was gradually building up to that. But let's talk about why this number is indeed 1 meter. All right? So let's talk about this interval between here and here. Okay? The initial velocity of the guy on the bike during this interval was what? Vi equals 0. What was his final velocity during that interval? 2. What was his average velocity during that interval? 1 meter per second, right? Hopefully, you can kind of see that just intuitively, right? That, well, if he started off at 0 and he ended up at 2, the average was 1, okay? But when we calculate averages, mathematically, what do? Add them all up and divide by the number that you have. Right now, how many velocities do we know? 2. If we add them together and divide by 2, that will give us the average velocity during a time when the velocity of the object is changing. Does that make sense? It works. Hold on to that. Page 1 of your packet. Right? Oh, I skipped something. I'm sorry. Good. Page 1 of your packet, down at the bottom, it says average velocity is easy to calculate. Look, it says so right there. I mean, if you can't trust this packet, what can you trust? All right. So, just like we did, right? Looking at this graph that shows the velocity of an object at a certain amount of time, right? Based on this graph right here, which you guys have in your packet, what's the acceleration of this motion? This is like a review question. What's the acceleration of that motion? Positive 1 meters per second squared, right? That's how much the velocity is increasing for every second that goes by. But if we look at just this 1 second interval, it goes from 1 meter per second to 2 meters per second, so the average is 1.5. Okay? Good there? All right. Now let's make a jump. Okay. So, graph that looks a lot similar, very similar to the graph that I just drew earlier, but this is a different kind of graph, right? It's what? position versus time. What can you tell me about the motion of this object here on the position time graph? It's constant. It's constant velocity, right? Because we said on this graph, the slope tells us the velocity. And we used this equation to represent that motion, right? That equation still holds true even if we're talking about an accelerated motion. Except this one right here, instead of looking at the constant velocity, we need to consider the average velocity of an object over that time frame. Now, for an object that's moving with a constant velocity, what's the average? That velocity, right? If something's going constantly at 4 meters per second, if you go 4 plus 4 divided by 2, you get 4, right? I know. I'm sorry. I didn't mean to blow your mind like that, Luke. All right? So technically, this equation looks like this. Okay? But we just talked about the idea that if a velocity is changing, the average velocity we can calculate if we know the initial velocity and we know the final velocity, and we just divide it by 2. Okay? So here, there we go. Here, we have an expression for average velocity. Here, we have an expression for average velocity, or we have average velocity as part of that expression, so we plug it in. So we end up with, not that, this one, right? xf equals xi plus 1/2 vi plus vf times t. That makes sense? How I got to that? Right. This expression right here gives us our second kinematic equation, which shows up at the top of page 2 of your packet. So at the top of page 2 of your packet, it says, average velocity is used in equations of motion. As long as the acceleration is constant, we can substitute in that expression of v average is equal to v initial plus v final divided by 2 anywhere that velocity showed up in an equation previously. And so now we have an equation where we can figure out where something is, final position, based on where it started, the initial position, and the initial and final velocity, even if they aren't the same. So we don't necessarily have to have a constant velocity. As long as it's a constant acceleration, we can figure it out. Okay? Good there? All right. So let's take a look here at quick example 3.7. All right. Quick example 3.7 looks something like this. It actually looks exactly like this. Okay, so quick example 3.7 says, a boat moves slowly inside a marina with a constant speed of 1.50 meters per second. As soon as it leaves the marina, it throttles up and moves with a constant acceleration of 2.40 meters per second squared. So part A says, what is the velocity of the boat after accelerating for 5 seconds? So let's establish a pattern here. A lot of this section and the 2 sections that come after this in chapter 3 are problem-solving sections. So let's establish the pattern and make sure we go through the steps. What is part A asking us to solve for? A final what? Final velocity. Anytime that velocity and after show up in the same problem, generally that's going to be a final velocity. Okay? So, A is asking us for V final. Things that we know in order to help us figure out the final velocity of this problem. What other information do we have to work with? Luke? The initial velocity of the boat is going to be what? 1.50 meters per second. Now, it doesn't say so specifically in this problem, so we get to choose, right? Luke, which direction would you like this boat to be traveling in? Okay, thank you. I just wanted to make sure that, you know. Sorry. All right, so we got that. Okay. Other things that we know, the acceleration, right? The acceleration tells us it's 2.40 meters per second squared. Okay, well let's finish up this first. Let's hold on, because there's one other thing we got to do with this, right? Physically, if the boat is throttling up, what is that going to do to the boat? It's going to make it go faster, right? What has to be true about velocity and acceleration if something is going faster? They have to have the same sign, right? So if this is positive velocity, this also has to be positive acceleration to make the boat go faster. And then the last thing that we know, the time. All right, 5.00 seconds, okay? So now it's a matter of finding an equation that has these 3 things that we know, plus the one thing we don't know, in order to figure out the thing we don't know. The first equation we looked at, right, relates those 4 things, the 3 that they were given to us, the one that we don't know, so we can solve for the one that we don't know. Do it. All right, it's good there? Okay. Do this. All right, here, here. Okay. Part B. Part B says, how far does the boat travel in this time? If it's asking us for a how far, what does that want to know? Final position, right? Where does it end up? Okay. Some things about this boat's motion don't change. For instance, it still had an initial velocity of positive 1.50 meters per second. It still experienced an acceleration of positive 2.40 meters per second squared. It still experienced that acceleration for 5 seconds. And then in the last problem, we found out that the final velocity of this boat was positive 13.5 meters per second. All right, Brett, go ahead. Right. In this case, yeah, because I probably could have made that a little bit more clear, but in this case, the intent of the problem was to handle the part when it's accelerating, because we're in the section in chapter 3, right? Section 3.2, which is motion with constant acceleration. So we're assuming that in these cases, this boat is going to experience a constant acceleration, and we can handle it with those equations, right? One other thing, even though we don't specifically, it doesn't specifically say in the problem, what else can we assume about this boat? We can assume in this case that the initial position is going to be 0. If it doesn't say specifically, and that makes our life easier, anytime we can make any one of the variables that shows up in an equation equal to 0, it just makes our life easier. Okay? Simran, go ahead. If you write it, then you can go, then that's okay, right? Like if you specifically say, assuming this, blah, 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 then I would give you credit for it, okay? Yeah. Like in that problem, if you would have said, assuming east is positive, I would have given you credit for +4. So, I would have. We just learned that this expression, right, this equation, takes into account the effect that the velocity has on the position for a certain amount of time, or the changing velocity has on the position that an object travels or ends up at, right? So, make our lives a little easier. This goes away, right, because we said the initial position was 0, right? So now it's just a matter of plugging in the things that we know and calculating what that final position is. What did you end up with? 37.5. Technically, Luke, what should we do with that 37.5? Make it positive. Okay? Now, one thing to notice. Did we have to use all the information that we figured out from the problem? We didn't have to use the what in this expression. We didn't use the acceleration to find out the final position. That's okay. We'll find out here by the end of this section here that we don't always have to use all the information that's given to us. We just have to find the right expression to get us what we need to know. Okay. Good there? All right. The homework that is on the calendar for this weekend, I'm going to change because it incorporates more problems than just the ones that we did here. There are more equations. We will finish up the equations on Monday. All right? Have a good weekend, everybody.